Section: Introduction. In this section, we have condensed our most creative works, surprising discoveries, and beautiful creations into written text. Large language models, LLMs, trained on this vast amount of text can learn a lot about the world and develop basic reasoning skills by predicting the next word in a sentence. However, this method is not very efficient in teaching language, world knowledge, and reasoning. State-of-the-art next word predictors need a lot more data than children to become fluent. We suggest that training LLMs to predict multiple words at once can make them learn more efficiently. Our approach, as shown in the main figure, involves training the LLM to predict the next n words from each position in the text all at once. This multi-word prediction method can help the models learn better and faster. Our study makes the following contributions. We introduce a simple multi-word prediction model that does not require extra training time or memory. We show through experiments that this method is beneficial for large models, and we demonstrate that multi-word prediction can make models faster during inference. By using multi-word prediction, we can train transformer models to be stronger and faster without any extra cost. We believe that our work will inspire new ways to improve the performance and reasoning abilities of these models beyond just predicting the next word. In standard language modeling, the goal is to predict the next word in a sentence. We extend this by introducing a multi-word prediction task where the model has to predict n future words at each position in the text. This leads to a different way of calculating the loss function compared to the standard next word prediction task. One challenge in training models for multi-word prediction is managing GPU memory usage efficiently. In our approach, we carefully design the forward and backward operations to reduce memory usage. By doing this, we can train multi-word predictors without using excessive GPU memory, making the training process more efficient. Section Summary. In this section, we introduce the concept of large language models, LLMs, trained on text corpora using next token prediction, which is limited in efficiency due to overlooking complex decisions. We propose a more efficient approach called multi-token prediction, where LLMs predict multiple tokens simultaneously, leading to improved sample efficiency and faster inference times. Our method involves a memory-efficient implementation that reduces GPU memory usage by adapting the sequence of forward and backward operations, allowing for more effective training of stronger and faster transformer models. Section: Inference. In this section, we utilize the proposed architecture for inference tasks. Our primary approach involves vanilla next token autoregressive prediction using the next token prediction head p_theta, x_t plus 1, mid x_t, 1, while disregarding other heads. However, we can enhance decoding speed by utilizing additional output heads through methods like blockwise parallel decoding and speculative decoding with Medusa-like tree attention. We conducted 7 large-scale experiments to demonstrate the effectiveness of multi-token prediction losses. We show that multi-token prediction becomes more beneficial as the model size increases. Additionally, the extra prediction heads can accelerate inference by a factor of 3 using speculative decoding. Multi-token prediction also aids in learning longer-term patterns, especially evident in byte-level tokenization scenarios. Our experiments consistently show that a 4-token predictor with a tokenizer size of 32K leads to significant improvements. The advantages of multi-token prediction persist even in training runs with multiple epochs. Pre-training with multi-token prediction losses and fine-tuning on the code contexts dataset results in rich representations. These benefits extend to natural language models, enhancing generative evaluations like summarization without significant regression on standard benchmarks. To ensure fair comparisons between next token predictors and end token predictors, we maintain an equal number of parameters in our models. We observe that the benefits of multi-token prediction increase with model size. Training models of varying sizes from 300M to 13B parameters on a dataset of at least 91B tokens of code reveals that multi-token prediction can significantly boost performance without increasing computational costs. By implementing greedy self-speculative decoding with heterogeneous batch sizes using X-formers, we achieve notable speedups in inference. For instance, our best 4-token prediction model with 7B parameters shows a speedup of 3.0 times on code and 2.7 times on text. Pre-training with multi-token prediction enhances the accuracy of additional heads, unlocking the full potential of self-speculative decoding. Training a byte-level transformer with 7B parameters on 314B bytes demonstrates the effectiveness of multi-byte prediction in capturing global patterns. The 8-byte prediction model outperforms next byte prediction, showcasing its potential for efficient training of byte-level models. Ablations on models trained on 200B tokens of code reveal that training with 4 future tokens consistently outperforms other models in various metrics. The optimal window size for prediction may vary based on the input data distribution, with 8 bytes being optimal for byte-level models across benchmarks. Section Summary. In this section, we introduce the concept of multi-token prediction losses and demonstrate their effectiveness through 7 large-scale experiments, highlighting their benefits in promoting learning of longer-term patterns and speeding up inference by a factor of 3 using speculative decoding methods. By training models of varying sizes and evaluating their performance, we show that multi-token prediction allows for significant performance improvements in large language models, especially at scale, and can lead to faster inference speeds, unlocking the full potential of self-speculative decoding. Section: Training for multiple epochs. In this section, we explore the training of models for multiple epochs. When we train models with multi-token prediction over several epochs using the same data, we observe that they still outperform next-token prediction models. Although the improvements decrease slightly, we see a 2.4% increase in pass at 1 on MBPP and a 3.2% increase in pass at 100 on human eval, while maintaining similar performance in other aspects. Additionally, we find that a window size of 4 was not optimal for 200 billion tokens of training in the app's intro scenario. Furthermore, when we fine-tune models with multi-token prediction loss, they perform better than next-token models for fine-tuning tasks. By fine-tuning 7 billion parameter models on the code contests dataset, we compare a 4-token prediction model with a next-token prediction baseline. We also explore a scenario where the 4-token prediction model is fine-tuned using the classical next-token prediction target after removing its additional prediction heads. The results show that both methods of fine-tuning the 4-token prediction model outperform the next-token prediction model across different evaluation metrics. This indicates that the models excel in understanding and solving tasks, as well as generating diverse answers. Notably, the code contests dataset presents the most challenging coding benchmark in our study. Overall, fine-tuning next-token prediction on top of 4-token prediction pre-training emerges as the most effective approach, aligning with the conventional strategy of pre-training with auxiliary tasks followed by task-specific fine-tuning. Moreover, we investigate the impact of multi-token prediction training on natural language tasks. By training 7 billion parameter models on 200 billion tokens of natural language with 4-token, 2-token, and next-token prediction loss, we evaluate the models on 6 standard NLP benchmarks. The 2 future token prediction model performs similarly to the next-token prediction baseline throughout training, while the 4 future token prediction model experiences a decline in performance. Detailed results are provided in the appendix. Additionally, we conduct evaluations on summarization and natural language mathematics benchmarks to assess the generative capabilities of pre-trained models with different training set sizes and prediction losses. The results show that multi-token prediction models with 2 and 4 tokens outperform the next token baseline in Rouge LF1 scores for both training dataset sizes, with the performance difference decreasing with larger dataset sizes. Further details can be found in the appendix. We also perform ablations on synthetic data to understand the factors driving the improvements in downstream performance of multi-token prediction models across various tasks. Through controlled experiments on training datasets and evaluation tasks, we demonstrate that multi-token prediction enhances model capabilities and generalization behaviors. Specifically, we show that induction capability is significantly improved by using multi-token prediction as the training loss for small model sizes. Induction refers to the ability to complete partial patterns based on recent context, and our experiments reveal that multi-token prediction aids in learning to transfer information across sequence positions, facilitating the formation of induction heads and in-context learning mechanisms. However, once induction capability is established, models can solve induction tasks locally with next token prediction alone. This suggests that while multi-token prediction may not be advantageous for certain benchmarks, it contributes to higher forms of in-context reasoning, as supported by our findings. Section Summary. In this section, we explore the impact of training models for multiple epochs and fine-tuning multi-token predictors. We find that multi-token training maintains an advantage over next token prediction, leading to improvements in performance metrics such as pass at K. Additionally, we investigate the effectiveness of multi-token prediction on natural language tasks, demonstrating its ability to enhance model capabilities and generalization behaviors, particularly in inducing reasoning patterns like completion of partial sequences. Section: Algorithmic Reasoning. In this section, we explore algorithmic reasoning tasks that go beyond simple induction. We conduct our experiments on a task involving polynomial arithmetic in a specific mathematical ring. The task includes operations like unary negation, addition, multiplication, and composition of polynomials. We aim to predict the coefficients of the resulting polynomials. During training, we vary the number of operations in the expressions from 1 to 5, which helps us adjust the difficulty level for both within the known range and beyond. Our evaluations are based on a fixed test set with 2,000 samples for each number of operations. We train two models with different sizes, one with 30 million parameters and the other with 100 million parameters. These models mimic large language models trained on extensive text data, which are also under-parameterized and cannot memorize all training data. Our results show that using multi-token prediction enhances algorithmic reasoning performance, especially in out-of-domain scenarios. Increasing the model size from 30 million to 100 million parameters does not improve accuracy as much as switching to multi-token prediction does. We believe that multi-token prediction excels in coding evaluations and small algorithmic tasks because it helps bridge the gap between training and inference phases. By assigning implicit weights to tokens based on their relevance for the text continuation, multi-token prediction focuses on crucial decision points. This approach emphasizes the importance of making the right choices at these decision points for generating high-quality text. In terms of information theory, training language models with teacher forcing tends to prioritize short-term predictions, potentially overlooking long-term dependencies in text generation. Multi-token prediction, on the other hand, considers multiple future tokens simultaneously, enhancing the model's ability to capture relevant information for upcoming text segments. This strategy increases the importance of mutual information between tokens, leading to more accurate predictions of tokens crucial for the text's coherence. Section Summary. In this section, we explore algorithmic reasoning tasks that involve polynomial arithmetic operations in a specific mathematical ring. By training models with multi-token prediction, we observe significant improvements in out-of-distribution generalization compared to next token prediction. Multi-token prediction helps models focus on important decision points in text generation, enhancing their performance on coding evaluation benchmarks and small algorithmic reasoning tasks. Section: Multi-token prediction in language modeling. In this section, we discuss the concept of multi-token prediction in language modeling. We argue that multi-token prediction is beneficial as it helps in planning, enhances representations, and prevents overfitting on local patterns that can occur during teacher-forced training. The technical approach proposed by others involves replicating the residual stream multiple times, whereas our approach allows for fair comparisons in terms of computation and ensures that the residual representations play a more direct role in the auxiliary loss terms. We also suggest model fine-tuning using multi-token prediction to achieve faster inference, although we have not explored the impact of this approach during pre-training. We conducted probing experiments to demonstrate that models focusing on predicting the next token can also predict subsequent tokens to some extent. However, our models, which are specifically trained for this task, outperform them in this aspect. Additionally, we noticed performance improvements in language modeling tasks when incorporating multi-label binary classification to predict the occurrence of vocabulary words in the future as an auxiliary learning task. Regarding self-speculative decoding, we are the first, to our knowledge, to propose a speculative decoding scheme for faster inference. Our architecture differs by replacing linear prediction heads with transformer layers while maintaining similarity in other aspects. By rearranging the forward-backward order, we can utilize all loss terms instead of randomly selecting one head for loss computation. We introduce a more detailed self-speculative decoding scheme that leverages the top k predictions of each head, rather than just the best one, and it is compatible with the multi-token prediction models we develop. In the context of multi-target prediction, we adopt a multitask learning approach where neural networks are trained on multiple tasks simultaneously to enhance performance on the main tasks. Incorporating auxiliary tasks enables models to exploit relationships between target variables, which can be advantageous even when the targets are independent. While there are possibilities for designing specialized architectures for multi-target prediction, contemporary deep learning methods typically employ large shared model trunks with distinct prediction heads for each task, similar to our approach. Multi-target prediction has proven to be effective in various domains, such as predicting time series with distant future time steps or learning from videos with multiple future frames or representations of future frames as auxiliary targets.